Okay, so for today, yesterday I sent you three open response questions. We talked about the last of the three, the wildebeest question. We talked about those two. What I wanted to do today is circle back to the two that were at the beginning of that packet. The first one is relatively straightforward, and I really hope that if you took a look at it, you were able to get through it pretty easily. When we're done here, I will send you my written solution. I'm not going to take the time to write down any solutions. I really just want to talk through how to go about them, and then you can read my solutions later. So let me put those up on the screen, and we'll take a look. Take a look at those guys. Chapter 3. Here we go. Okay, so this was the first one, and like I said, I don't really anticipate you seeing a question exactly like this. I don't envision you having to draw a scatter plot. I think it takes a fair amount of time and doesn't demonstrate a lot of different skills. So, but I think there's value to creating the scatter plot. And what you'll see in my solution is I just drew, I put the data in the calculator because you're going to need to do that to answer part B. And so what I did, I just printed off a copy of what you would see on the calculator screen and use that. But it's pretty straightforward. The real question is which do you make the response variable and which do you make the explanatory variable? You always have to answer that question. And so the way to go about that is, does age explain height, or does height explain age? And I think that in this case, the explanatory variable is obviously age. So it'll go along the x-axis, and height goes along the y-axis as the response variable. So the scatter plot, I think, is pretty straightforward. Again, to find the equation using the calculator, we would have to put these in. And I tell you what, let me just go ahead and do that real quick. It won't take us long to get that done. I want you to be able to see and be familiar with how to handle regression analysis on your calculator, just in case you feel more comfortable answering your question with that. Okay, so we got to get the data in the list, and so we'll talk about lists 3 and 4 here. So list 3, we'll put in as the explanatory variable, and list 4 we'll put the response variable. Okay, we'll assume we got that right. And to make the scatter plot, again, we'll do stat plots. We'll just use one. We'll pick scatter plot. Now this time we need list 3. And for the y variable, we need list 4. We'll graph that. Always hit zoom 9, and there you go. You've got a graph that is fairly linear in scale, and again, you can hit the trace button and follow the data points from left to right. So that should be enough there. And then in part B, it says use the calculator to find the equation. So we got to go back to stat, calculate, and we want to do linear regression, but remember we're going to skip over choice 4 and we're going to cursor down to 8 or just hit the 8 key. We'll do a plus bx. The x list is L3, y list is L4. And we'll calculate that, and then here's our value. Okay. And so a couple of things I want to talk about this particular regression line and the values for r and r squared here. The regression line is pretty straightforward. Okay. The y value, the y-intercept is 71. And again, this is clearly a case where the y-intercept doesn't make any sense in context, because what it says is the person would be at 0 years old or 0 months old, would have a length of 72 centimeters, I think. I think it's in centimeters. Yeah, in centimeters. And so if you divide 72, let's jump out of here real quick. 72 divided by 2.54. 28 inches long, and that it's pretty rare that you you have a baby that's 28 inches long at birth. So again, that one doesn't make a whole lot of sense. So let me get back to the results here. Now, you might be asked to interpret the slope of the equation, and what that means is for every 1 month of age, the baby's length or the person's length increases by 0.38 centimeters. Let me double check. That is centimeters. Yeah, for every 1 month of age, Sarah's height increases 0.38 centimeters. Okay, so that's how you would interpret that. Now, we would look at R as the strength of the correlation, and it is incredibly strong. An R value of 0.99 is incredibly strong. So if we were to be asked to describe this scatter plot with an R value of 0.99, we would say that it was a positive, linear, very strong association. And if you remember the graph, there weren't any outliers. And so that is a very, very strong correlation. One that you rarely see in the real world that strong. Now, yesterday we closed the class talking about R squared, and R squared talks about the percent of variation that's described by this regression of height on age. And you can see that 98.9%, so practically 99% of the variation that's seen in the data is described by this regression. There's practically no other variable that has any influence on Sarah's height except her age. And so R squared, again, being being a very, very high number, very, very close to 1, describes that this is an incredibly powerful regression. And then the last question here, use your regression line to predict Sarah's height at 40 years old or 480 months. And it also says convert your prediction to inches. I did that because most of us wouldn't really understand what this value was in centimeters because we're all American. When you do that, obviously at 40 years old, we know that Sarah's not going to continue to grow in a linear pattern until she's 40. And so you get some ridiculously high number. In fact, Part D says that, and it says it's impossibly large. What happened? And the answer we would give there is 480 months is well past the range that the regression model was used to create. And so therefore, using it to predict a height outside that range is extrapolation. And we would, under no circumstances, expect Sarah to continue to grow at the same rate until she's 40 years old. So that one is pretty straightforward, I think. So again, though, it's good practice for using the calculator to do your calculations. And it's good to have that in your back pocket to know how to do those if you feel like you need to. But again, I don't anticipate you needing to. I think more likely the scenario you're going to be given, like in the second question here, you're going to be given a scatter plot. Here's the regression line. And you'll probably even be given the regression equation. But maybe not. I don't know. The good thing about this question is there's really not there's not a lot of calculations to do. And so I think the questions that are asked here are reasonable and fair for what you might see next Friday. So the context here is biological silicon left behind at the bottom of a lake in Alaska. Contains certain isotopes, and you remember from chemistry that a certain percentage of all of the silicon molecules, I think, are radioactive, and so we can find them. We can find them here. The farther you drill, of course, the deeper into the past you go, and so here is a scatter plot of data in these age ranges. Okay, and so the first question is pick out the unusual point in the scatter plot, and then what's unusual. Well, again, I think I've said this many times before. I think Stevie Wonder can pick out the unusual point. It's this guy here. And so how would we describe that? And I would describe it in a lot of ways. You could describe it quantitatively, and what you might say is let's see, ratio, indirect measure of moisture as we drill down. Okay, so for this data point, for this particular isotope, it has an unusually high amount of silicone. Might be one way to describe it. Another way to describe it is it has a very large residual because it's far from the prediction line. But you want to point out that the value is around negative 19.4 and 350. Identify the coordinates, either just write them down up here like you would a point on an Algebra 1 graph or in your discussion. But it is very far from the prediction line. That's the bottom line, is what's unusual about this point. And so in statistics, we identify really two types of values. that affect or impact regression lines. An outlier is a value whose x, or a point whose x value is far from the rest of the other points. Okay, so if there were a point way over here, we would call that an outlier. Well, this value is really not an outlier. Its x value is in line with the pattern of the rest of the data. And so we would call it, another term you might use here is an influential point, because it has a very high residual compared to the rest of the values. You can see the rest of the values are pretty uniformly distributed around the line. And so you might describe this as an unusual or influential point, because it has such a high residual. Okay, so that's part A. Now we need to talk about what happens if we were to take this point away, just ignore that data point. What happens to the correlation? We don't have any values here, so we can't talk quantitatively about the correlation, but we can certainly talk qualitatively. So what we have here is a moderately strong correlation that is certainly linear in nature, and the slope is negative. So the R value is some negative value. And so if we take this point away, the correlation gets stronger. In other words, it gets closer to -1. So whatever it is in its initial state, when we take this point away, the value for correlation will get closer to -1. And I think that's probably the best way to express that, is that it gets closer to -1. Don't say that it becomes more negative, because -10 is more negative than this value, and the correlation couldn't be -10. The correlation is a value that varies between -1 and +1. So make sure that if you need to describe what happens when this point is removed, you just say that the value will get closer to -1. While saying it becomes more negative is true, it is less precise. And so I want you to be able to describe it as becoming closer to -1. And then interpret the slope and the y-intercept of the least squares line. Okay, so again, we're not given the values for A and B here, so we don't know the slope, we don't know the y-intercept. But we can describe the effect. If this guy goes away, then these points that are below the line here are going to pull this line down, okay? And so in this case, it would be appropriate to say that the slope does become more negative. Slope can be any value. It's not constrained to a -1 or +1 range. So to say that the slope becomes more negative is entirely accurate and correct. And then if the slope of this line becomes more negative, in other words, it's being pulled down by these other points, then the other end of the line is going to creep up this way. And so what we would say about the y-intercept, the value for the y-intercept will increase to closer to 300. And you're not saying that it will be equal to 300. You're just saying that it increases closer to 300, or in the direction of 300, or nearly 300. Something like that will be accurate enough in this case. And so this point here, again, it shows that regression analysis is not resistant to unusual points. We wouldn't call this an outlier. We would call it an influential point, but the mere presence of this one line or this one data point drastically affects this. I think somewhere I took this data and I tried to calculate the regression line just using the data points and with and without this one. If I can find that analysis, I'll send it to you. I may not have ever really kept it. I think I just did it for curiosity's sake. But the presence of this one influential point strongly affects the correlation. It affects the slope. It affects the y-intercept. And so I wanted to make sure we walked through this one and talked about it so that you be prepared to answer questions like this, because you don't have to push a single button on the calculator. And so I think it would be reasonable that you might be asked a question similar to this. Again, I will send you my written solution after we're done here, and you can look it over. But that's basically the gist. Okay. Any questions? It all makes sense. Pretty straightforward. Okay. Well, then I honestly, I think we have thoroughly covered regression that you might see on the exam. We've thoroughly covered regression, quite honestly. There is one more topic that is later in the textbook, and it's been, because of the change in the schedule, that particular topic has been lopped off of the test, so I don't expect you'll see it, so I'm not going to address it here. What I'll do is pick out a previous AP question. I'll send it to you, and it will be more like what I expect you to see. There's the scatter plot or residual plot. I think the regression line, equation for the regression line is given to you. And so you're asked to do, describe the distribution, calculate predict a value somewhere along here, questions like that I think you're very likely to see. And then tomorrow we'll take up another question, probably about probability. I mean, we haven't talked about probability for a while. And then next week, I'll go, there's some really good questions about conducting an experiment and using blocking or other sorts of techniques to divide the data in an experiment or an observational study. We haven't talked about those since that chapter either, so I'll pull in a couple of those questions just so that it's familiar. Not a lot of calculations involved in those type questions. So again, I think you might be asked something in that range or along that line. So that's my plan going forward. Again, if there are other ideas, other topics you want me to cover, just feel free, send me a note, and I'll be glad to pull something out. Okay. All right, gang. That should do it for today, unless y'all got questions. Good seeing you again, and we'll go ahead, Riley. We'll plan to get together at 1. If it's just you and me, we'll make it short and sweet. Maybe some of the others can join us. We'll see. Okay. All right, y'all have a great afternoon. We'll see you tomorrow.